So, hello everyone, and welcome to today's episode of Carbon Experts Live. So, while people are still joining, we'd love to see where our audience is coming from. So, please jump into the chat or comments and let us know where you're viewing us from. So, today's episode is going to be quite exciting. We are going to discuss about the growing importance of decarbonization of steelmaking, and we're here today with Marion Charlier, who is an advanced building solution and sustainability lead at ArcelorMittal. Okay, so I don't see any comments yet, so please do share where are you coming from? Yes. So hopefully we're going today to have a lot of great insights from Marion on the topic. So before we get started, I want to introduce you our host, who is Johanna Järvinen, LCA and EPD expert at One Click LCA. And throughout the whole session, we will be collecting questions, and the questions will be answered by the end of the discussion. So here down on the right corner, you can see the questions section. So if you can post your question there, would be great, but we will still be monitoring the chat and collecting your questions and comments. So just a few housekeeping rules and what to expect. So we will start by having a conversation with Marion and Joanna about the future and the path to zero carbon steelmaking, which will be followed by our questions, and we will conclude with the live Q&A by the audience. So now I will be gladly handing the floor to Marion for her presentation and then to Joanna.
All right. Welcome everyone, and thanks for joining our webinar. I will now try to share the screen. Hopefully it works smoothly. All right, hope you can see the presentation in full screen.
We can.
Okay, good. So hello everyone, I'm Marion. I'm a structural engineer working at ArcelorMittal. I've worked a couple of years in R&D, mainly working on structural fire engineering topics. And in 2021, I have joined the Steligence engineering division of the group, which deals with technical assistance in a sense that we try to advise and to support our stakeholders, architects, engineers, authorities, contractors, developers, to make the best of our steel products in their projects, so we can advise on different topics, and also sustainability, of course. And it's in that sense that I'm going to present to you today what is the steel industry doing in terms of decarbonization, also what is ArcelorMittal doing in terms of decarb. And outside of this, talking more globally speaking, as a structural engineer, how can we proceed to try to make, to really decrease as best as we can the embodied carbon of our projects. So first, I wanted to start, of course, with the basics, which is understanding the emissions of steel and our leadership ambition at ArcelorMittal. So to start with, it's really important to stress that there are different ways of manufacturing steel. There are different production routes. Each production route has its own carbon footprint, and also because the mechanism behind is different, the strategy is different if you want to decarb the production route. So you can see here on the slide that we start with what most people have in mind when we talk about steel. It's the blast furnace production route. Following that route, we're using as main inputs iron ore and coal. The iron ore is present under the form of an iron oxide, so we have oxygen which is tied to the iron, and we want to recover the iron only and remove the oxygen, and to do so we use coal as a reductant. And this is why this production route is quite intensive in terms of carbon emissions. So as a worldwide average, we can consider roughly 2.5 tons of CO2 equivalent per ton of steel. This production route is usually referred as a primary steelmaking production route because we make steel from iron ore. It's also the case for the second production route, which is called DRI, for direct reduction iron, followed by an EAF. Here we are also using iron ore, but instead of using coal to remove the oxygen from the iron, we use natural gas. And here, in terms of worldwide average, we can consider roughly 1.25 tons of CO2 equivalent per ton of steel produced. So roughly half of what we had just before with the blast furnace. Then third route here mentioned on the slide is the electric arc furnace. And here it is not anymore a primary steelmaking route, but a secondary steelmaking route because we are recycling steel waste that we call scrap. This steel waste can come from the construction industry, of course, but it can come from any type of industry. So it can be machinery, old cars, old washing machines, and so on. So we use that waste, and thanks to an electric arc, we are melting that waste and remanufacturing steel again, because steel can be recycled over and over without losing its mechanical properties. And here, in terms of emissions, we're once more roughly dividing by 2, reaching roughly 0.6 ton of CO2 equivalent per ton of steel produced. And when we are using renewable electricity, we can once more divide roughly by 2 the emissions. So it is very important to understand these 3 main routes which are existing today, because depending on if we're working with a product which is made from one route or the other, the carbon emissions will be different, and the technologies and the developments that we need to put forward to decarbonize are different as well. So now I will talk more about what we do within ArcelorMittal to reach our decarb targets as industrial roadmap. And this industrial roadmap is based on 4 main pillars. The first one is steelmaking transformation. It means that we are really about to shift some of our production sites. We are willing to go from the blast furnace production to the DRI. So if we come back to this slide, you can remember that the DRI has roughly half of the carbon emissions than what has the blast furnace.
Sorry, Marion, can you hide the button underneath, because we can't see the carbon values?
Oh, there you go.
Thank you.
Is it better now? Yeah.
Yes.
So yeah, the plan is to switch to DRI. But not only because, okay, this is of course better, as you can see here on the values, but the extra step is to change the reductant. So instead of using natural gas as a reductant, the aim is to use hydrogen. Today, hydrogen is most commonly made from petrochemistry, so it's not a real sustainable alternative, but there are many ongoing developments to produce what we call the green hydrogen, which is obtained through water electrolysis. And so using that hydrogen as reductant, we can really decrease the emissions from this production route. So that's the first pillar. Then the second pillar is more related to what we call the energy transformation. Knowing that changing a production site from a blast furnace to a DRI take a lot of time, there are still improvements that we can implement in our blast furnace sites, and I will give you an example just after. Then there is the use of scrap that we try to maximize and to use wisely at the right place, because also if we look at this chart, we see that the EAF, the recycling, has today the lowest carbon footprint. And also quite logically speaking, it makes sense to recycle a material if you can. And the fourth one is the use of clean electricity. So now going a little bit more into the details of the different pillars. Steelmaking transformation, actually, I already told you this, that, okay, we're working on switching from natural gas to hydrogen, but also sourcing the green hydrogen. And for this, I think it's important to mention that there are synergies and collaboration with local governments to produce this green hydrogen. So it's not only that we rely on an existing source, we are also involved into generating that green hydrogen. Then in terms of energy transformation, I told you that I was going to give you an example. And this is the one that I have chosen, which is existing today in our mill in Ghent in Belgium, where we are actually capturing the blast furnace gas and transforming it into ethanol that can be used in various applications, but for example, the transport. So this is an example of improvements that can be brought to a blast furnace site, which is today the most intensive production route. We continue, increase use of scrap. As I told you, of course, the scrap has to be recovered as we can to the best of our ability, and to make sure that we use it wisely to make new steel out of waste. And this is a quite fascinating feature of steel, that it can be recycled indefinitely without losing its mechanical properties. So knowing this, it would be a pity not to recycle the scrap that we have. And as a link to the use of clean energies, I wanted to talk to you briefly about the xcarb Innovation Fund, because I think this is quite unique. The company ArcelorMittal has committed itself to spend $100 million a year into other companies than ArcelorMittal, but these companies are necessary to reach our carbon targets, because as you may have understood, most of our developments are really relying on the use of energy. We're talking about hydrogen, we're talking about renewable electricity, and we need to make sure that we're able to produce that extra demand of electricity, and we need to make sure that we're working together to achieve these targets. Because even though we are launching a lot of initiatives in-house, because we're still manufacturers, and there are things which are our responsibility that we need to take care of as steel makers, there are other things. It is not our, let's say, our knowledge and our part of our skills. So we need to make sure that we work with the right collaborators to make that happen. So now, for the next slides, I would like to come back on the EAF production and on the recycling of steel, because within all of these initiatives that I have told you, so there are many things ongoing, but I think it's important to stress that not everything will be ready at the same time. So first of all, it's really important to understand that both primary steelmaking and secondary steelmaking needs to decarb. We need everything that I told you, like the switch to DRI, the use of efficient energies and so on. Everything needs to be deployed. But you can understand that, for example, switching one manufacturing site from a blast furnace to a DRI takes a couple of years also to source the green hydrogen. So if today some customers are contacting us to reduce the embodied carbon of their project, we would advise them to work with our branch, which is called Recycle and Renewably Produced, which covers all of our EAF manufactured products, meaning that we recycle them and we use renewable electricity for that. So for example, if I take our sections that we manufacture here in Luxembourg, We use 100% scrap and renewable electricity. And so doing so, we are able to bring the global warming potential for the production stage as 333 kilos of CO2 equivalent per ton of steel. So if we compare to the average for the global steel industry today, it's the difference is quite significant. And within this xcarb, recycle and renewably produced family, I just told you about the sections now that we make here in Luxembourg. In Luxembourg, we also produce sheet piles. But there are other products that can be made through that production route. We have the hot roll coils that can then in the end be used to make some steel deckings, some facade. We have some rebars, heavy plates, which are used in the construction, but also in the energy sector for wind farms, for shipbuilding, and so on. So yeah, this was the first part really related to steel making, what is the steel industry deploying, and also what we are doing within ArcelorMittal.
Thanks, Marion. You mentioned there quite a few ways to decarbonize steel making. Apart from those you mentioned, are you aware of any other initiatives in the wider industry or yourself that people are maybe starting to look at the moment, which are not ready but have?
Yes. So there is one more path that is being investigated at the moment. It is the direct electrolysis of the iron ore. So, as I told you, when we make primary steel making, and so we use iron ore, which is present under the form of iron oxide, we want to remove that oxygen from the iron. In the blast furnace and in the DRI, we do so by using a reductant, which is either the coal, either the natural gas, or the hydrogen. But it is also possible to actually, let's say, detach these atoms one from another using direct current, using electricity. So we do not need the use of coal, natural gas, or hydrogen. And there was a research project which was funded by the European Commission. So it was done under the scope of the Horizon 2020 research program. And it was quite promising. And so based on that, there are some developments which are being taken to pursue the consideration of that steelmaking route. So I think, if I'm not mistaken, that there were announcements made that the first plants using that technology would start in 2027 or 2028. So it's not today, but it's also not too long in time.
That seems to be quite close. I mean, it takes a couple of years to even build a factory. So yeah, that sounds promising. All right, I'll let you carry on. Next.
Second block of today's contribution is about decarbonizing the built environment and how steel structural solutions can support sustainable projects. So here we've covered the more material science, material part, and we enter the more structural engineering part. So I wanted to start with this LETI guide, which has been published in the UK, where some targets in terms of kilo of CO2 equivalent per meter square are provided depending on where we are in time. And if we take as anchor, as targets, what they provide for best practice 2030, we see that we need to fall below 350 kilo of CO2 equivalent per meter square. So also, if we have a look at the little chart at the center of the slide, we see that, for example, for an office building, roughly the superstructure accounts for half of the emissions. So going from these 350 kilos of CO2, we take half, and we are roughly, we have this target of roughly 170 kilos of CO2 equivalent per meter square. So if we start from that, We deduct the slab as a first step that we assume to be at roughly 70 kilos of CO2 equivalent per meter square. And we see that for the frame, we have an allowance of roughly 100 kilo of CO2 equivalent per meter square. So now we look at the carbon intensity. If once more we take an office building as an example, we see that, of course, depending on the height of the building, we will have a different steel intensity. So as an example, we can take the steel frame to a high-rise building where we have roughly 90 kilos of steel per meter square. So now we have several possibilities in terms of carbon intensity, either with an average. So here we have roughly 2.5 tons of CO2 equivalent per ton of steel, which is what we have, for example, for the blast furnace route, or as average in some parts of the world. And then we would end up with 221 kilo of CO2 equivalent per meter square, which is above the target that we have. But now if we use the xcarb recycled and renewably produced steel, we see that because the carbon intensity factor is much lower, of course, we reach a much lower number, which is actually way below our target. So we're okay with that. But what we can do instead of using xcarb everywhere, let's say, is to set an embodied carbon target. So here we have our 100 kilos of CO2 equivalent. Then we calculate the steel intensity. We know it here for our office high-rise is 90 kilo of steel per meter square. And we will calculate the average carbon intensity required for the steel sections. So here we see that we would need to reach a carbon intensity of roughly 1.10. And so to meet that target, we can calculate the minimum percentage, the minimum amount of xcarb required to meet the target. So here we would see that based on these numbers, we would need 64% of xcarb to meet the target. So this is the kind of reasoning that we can apply when we are looking at material only, which is good. But choosing low carbon material is clearly not sufficient. As architects, structural engineers, we need to couple this to a clever design, also trying to reduce to the best of our capability what we can build. So I assume most of you are familiar with this hierarchy where we try to build nothing and then build less. We need to build clever. So for example, when it comes to steel structure, quite simple but yet effective measures would be for the members where it makes sense to use high steel grades. For example, for the columns, which are driven by resistance, then we're making the superstructure lighter. We need steel sections which are globally smaller. We have less material, and so we're making carbon savings. And we're not even talking about low carb steel here. We're just making material savings. But on top of having a superstructure which is lighter, we will also have less foundations. So all of these things need to be taken into account as a whole, so really having this holistic view of the project. Another example that I can mention is the use of cellular beams. So these beams in which we have holes in the web, because from a certain number of levels, we can actually gain one level. Because we reduce the floor to ceiling distance. So we reduce the total height of the building, which also translates into savings, money, but carbon when it comes to facade, staircase, and so on. So all these things need to be carefully thought when we prepare the project. So talking here, for example, about the columns, it's a simple but quite straightforward and clear example. We consider a steel column subject to actual loading, buckling length 3.5 meters. We make a first pre-design, and we see that if we make our design in S235, so very basic steel grade, we would require as section an HEM 280, which is almost 200 kilos of steel per meter. But then we just change the steel grade and we go for S355, which is also quite basic actually, but which is better than S235. Now the required section is smaller. It's an HEB 320. So we're reducing the weight of the column. We're making savings in terms of carbon. And then on the third data, we're actually accumulating two things: the use of high star 460, so an even better steel grade, and xcarb. And okay, here we are combining these two, so the reduction is even bigger. Here is another example, but which is similar, starting from S355 for column. First, we do a smart design. That's the first step to do. For example, here using a high star 460. And then smart specification, we use the xcarb steel, and we reduce the carbon footprint of 91%. We have reduction of CO2, but we also have reduction of cost. So that is also important to consider, of course, that we have different constraints when we work on a project. We have the sustainability to address, but we also have a budget to respect, maybe speed of mounting, fire requirements, all these things which needs to be kept in mind. Another example here for a project where we have received from our collaborators a first pre-design initial solution, steel frame, based on S275 megapascal steel. And we have very simply switched to high star for the columns and the use of xcarb. And also, if you can notice on the option on the left, there was a column also at the center of the bay that we removed in the proposed layout. And so from this, we could quantify the Scope 3 savings and highlight the benefits in using that new layout. Here, going on other aspects of the buildings with steel, so far I have mainly talked about steel frame, but there are other products that can be obtained in xcarb. And you can see here some examples where in the blue circle, you see the gains that you can achieve with what we call the material optimization. So we're not yet talking about low carb steel. And then the green circle provides the gains when we combine material optimization and low carb steel xcarb. In terms of structural system, I have already mentioned the cellular beams, which to me are a really good example of an innovative solution that we can deploy. We're taking one beam, cutting continuously through the web. We separate the two parts, we reassemble them by welding them, and we end up with a beam which, let's say if we take the original beam, we now end up with a greater moment of inertia, but with the same weight than the original beam, which has a lower moment of inertia. Also, the cellular beams are interesting if you want to pass, for example, ducts MEP into the openings. Something that I would like to mention as well, because I personally feel that it is really important, is to play the strength of each material. So far I've been talking about steel, but for me it is really important to combine materials and to place them where they are the most needed and to use the right material at the right place. So of course we talk about composite. Steel and concrete composite structures are quite well known and quite well deployed because we really put the material where it is needed. But we are also working at the moment on steel plus timber solutions, which exist for quite some time as non-composite members. For example, we just put a CLT slab on the lower flange of a steel beam. But now there is some research ongoing at the University of Luxembourg to demonstrate some composite action between steel and timber, which is really, let's say, an extra step that we can achieve in terms of structural optimization. So yeah, that was my input when it comes to structural system. I know it's a bit of a rough overview, but we're a little bit short in time, and of course, if you have some questions, I'm available to answer.
There were some good ideas there for designers. if you work with the designers in industry currently, do you think they all, or what would you say, how they are designing now? Like, does everyone you have a carbon in their mind when they design, or is it more cost savings that they think if they need to reduce materials? If you compare like 2 years ago, does people normally think about the carbon impact, let's say in Europe, or are they still not unsure, or not? It's not their consideration.
We definitely see a change throughout, by comparison to what we were doing a couple of years ago. A couple of years ago, the questions related to sustainability were very rare, but now they are actually most of the questions that we receive. So definitely there is a shift happening, which is really good. And it's also good to see that people are taking more interest in how materials are manufactured and what are the challenges that the industry is facing. But I would say that we still see some differences across the different countries in Europe and also overseas, because what is really driving the shift is the regulations which are put in place. So if in some countries you have a regulation that makes the LCA of a project mandatory, and regulations which provide targets to meet when it comes to embodied carbon thresholds per meter square, then definitely the customers, the engineers, the architects, everybody will be facing the same challenges and fighting to consider that constraint quite early stage. But in other countries where it's not mandatory, I will not say that it's not relevant, but it's more like a nice to have thing. But luckily, I would say that the end customers are more and more aware of the challenges that we're facing. And even though it's not made mandatory by the country, we still see some people willing to take the extra time, to spend maybe the extra money to reach the targets.
And I assume then regulations are more localized to Europe, so the Europeans are more in thinking more carbon than others, or is that fair to say?
I think so, but I don't want to get mistaken, because I'm also more working at the moment on the European market. Okay. Yeah, I think that
let's not generalize then, but that's what we.
Yeah, I think that definitely in Europe we see a lot of push and a lot of regulations being prepared. But overseas, it's also, it has to be noted that in some countries where there is no regulation, we receive a lot of requests when it comes to support to decrease the embodied carbon of the structure. So yeah,
something like
it's a good trend. It's a good trend.
It's like the UK doesn't really have a central regulation.
Exactly.
London-centric. Right, okay. You had some other items of some examples as well.
Yes. The next block is what I call closing the loop, facilitating steel reuse. Because so far we've been talking a lot about LCA and decarb of the steelmaking, but I personally feel that a dramatically important topic when it comes to the sustainability of the built environment is the circularity. So I wanted to briefly introduce a research project which is called Reduce, which was finalized in 2020, so it's not that new. And you can see here on the slides the members, the participants in that research project. And the purpose was really to focus on the reuse of steel structure and more importantly on the demountability of steel frame structure and of composite slabs. So the basic of this research was to work on modular design, to think of building as multiple of basic modules. And from that we could work with a set of standardized sections, so a lot of prefabrication, then make sure that we designed for disassembly so that we're able to dismantle the buildings and to recover the elements and to rebuild from that. So for example, one part of this project was focused on adjustable connections. So if we assume that we work with standardized beam length, actually we could have some issues in reusing that beam if then in the second life of the building the columns have different size. So that's why they came up with these adjustable connections. So the principle is really, as for the Legos, okay, we're working with standardized beam length, which are a multiple of the basic grid module. Then we remove 2 times 200 millimeters, and we work with these adjustable connections, which have been tested in the lab and also numerically modeled to make sure that we can apply the design based on that. And also, the second really interesting point which has been developed is demountable shear connectors. Because as I told you, composite structures are really important when it comes to using less material, because we are going to use materials exactly where they're needed. But usually composite steel concrete composite construction is non-demountable. We can do, for example, a steel beam with a hollow core slab or like a concrete slab just put on top of the beam, and this is then easy to dismantle, but we're not activating the composite action. While here they have developed these special demountable shear connectors with bolts that allow to activate the composite action, but still to be able to then remove the slab from the beam. And from this research project, there was a pilot project which was built just next to the University of Luxembourg, which was called La Petite Maison, because it's supposed to be a petite maison, so a little house in English. It has been built and it has been dismantled. So the demountability character has been showcased. And if I'm not mistaken, they're going to rebuild it on another location soon. So this will be really a pilot project. It's a small one, of course, but it's important to highlight that what has been prepared in the research can be deployed in reality. Just for your information, the University of Luxembourg is now working on the same principle, but with steel and timber. So also activating the composite action and also allowing the dismantling of the elements. So this is ongoing. So definitely this is the first step, the design for disassembly, because we would like all to reuse the elements. And sometimes we have people coming to ask us, okay, where can I find reclaimed old steel beams? Some stockists have some, and you can find them maybe in bigger quantities in some countries than others. But I would say that if we want to enrich that stock of reused old beams, we first need to make buildings so that we design them to be demountable. Because otherwise it's a little bit the chicken and the egg. If buildings are not designed to be dismantled, then most of the time people will just take them down as usually, crushing the concrete, cutting the steel, bringing it back to the scrapyard. So there is a certain effort which needs to be deployed if we want to make sure that we can easily recover the steel beams. But let's assume that we do that and that we deploy more and more these kind of technologies. So we do have quite an important stock of reclaimed steel elements. There are some guidelines which have been prepared, and some people are still working on that at the moment, to help you adapt your design equations if you're working with reused structural steel. So for example, there is here the guide that was published by the SCI in the UK, which is very well done because it's really written as a protocol. So it's really meant to be used in practice. It's not just like theory, it's really made for practitioners. And I wanted also to briefly present this project, which was built in Belgium, in Louvain-la-Neuve, where they have made this small office building based on reclaimed steel and timber elements. The timber elements are new, they're not reclaimed, and also there is no composite action here, but still it's a good example that reusing steel can be done. When we talk about circularity, we can also talk about what we'll design for adaptability. So for example, if we use large spans. So some people may, it may be subject to debates that, okay, if we have bigger spans, maybe we will increase the embodied carbon, which is true in some cases. But on the other hand, if you make sure that you have a lot of volume and quite a flexible space, it means that you have some kind of flexibility when it comes to the use of the building, and that this encourages the fact that we can ensure that the building will live longer, which is really what we try to do, because unfortunately today there are still many buildings which are being demolished, even though they haven't even reached the 50 years lifespan. So this was about circularity. There are many things which can be said, and to be honest, there are many very interesting contributions from academics and research centers that I would like to present. So if it's a topic that is of interest for you, I will be glad to send to you their research papers and their achievements in that field.
Thank you. That reduced research is obviously very interesting. If you can just move a building or parts of it in some other places and rebuild, I think it has been done in some other ways too. Do you think there's a limitation on the size that you can build using these principles?
I would say no, in a sense that all the systems that are being deployed are not, the development are not constrained to a size. But it's true that in reality, it has been built so far only for this Petite Maison project. So it has been built only for a small scale project so far, but definitely this could be scaled up. There is no scientific reason why it would not work, because all the systems have been thought as usual structural systems, so not only meant for small, tiny houses. But so far, this is the only real project that we can refer to. If you want to build a bigger one, I will be interested.
If anyone is interested, contact and we'll get it happen. All right, then some more about embodied carbon.
So this is the last piece of contribution that I wanted to mention today. Is what we call the co-engineering approach, the global approach that we push for. So first of all, I wanted to use a slide that was prepared by a person that I admire a lot and that I happen to work with sometimes, Lee Frank, who's working in Luxembourg. And last week we participated together in a seminar, and she came up with that slide, which I thought was very accurate, that we really need to keep in mind that if we want to reach a low carbon project, we need to start early. We need to work with a full team. We need to educate all the stakeholders. So not only the engineers, but also the end customers, the general contractors, the demolition companies, everybody which is working in the construction field and which is also going to, let's say, receive the project in the end, to collaborate, to iterate. I think we are working, we're deploying things, and we're still somehow at a very early stage of our developments, and we should not be afraid of challenging what we do, try again. And of course, it takes more time than if we do business as usual, but it's what we need to do if we want to really reach efficient targets. To take time to compare, so to prepare different structural variants, to really take the extra effort to consider different solutions, to set targets, and to share the results, because we can learn a lot from others. So it would be a pity if we were doing like the best project ever, but we were not talking about it. Here, just to give a word about what we do here, as I told you at the beginning of the webinar, within our department Steligence, we are providing free technical assistance. So we can support you when it comes to using composite systems with steel, structural fire engineering, LCA, FEM modeling. So we are really willing to support you in this. And when we say that we provide technical assistance, we really want to come up to that, let's say, approach and to that thinking that we want to start early, to work with you, to collaborate, set targets, and so on. And here is a little bit what we try to deploy when we work with our collaborators and what we advise others to do as well. So first of all, to enable high performance design, not to over design, which is something which is quite regularly done today. To use less but stronger steels when it makes sense. So for example, for the columns, we can, as I shown you with the columns examples, it can lead to direct CO2 savings, even if we're not talking about low carb steel. To understand where is the embodied carbon in the project, so to run some kind of hotspot analysis, because you will see that some elements will be an easier win than others, and so maybe we should start with these. To understand how steel products are made, because it's only if you understand the manufacturer, but also the supply chain, that you will be able to really make relevant savings. And of course, here I'm talking about steel, but this applies to any other material. And to act early and work together. Time can be the enemy of sustainable. Of course, the earlier we are starting the work together, the greater will be the gains that we can achieve. And here, okay, there is a little bit of redundancy, but still I think it's really important to insist on this. So suggested approach to tackle the climate emergency and reduce the embodied carbon of your project. Number one, understand how steel products are made. Today I gave you a little overview, but I would really strongly encourage you to engage communication with the manufacturers. Don't be afraid to contacting us or other manufacturers and to ask questions. I think it's only if everybody understand what are the challenges, what are the opportunities that we're facing, that we can really move forward. Then design and plan. Challenge the brief, consider several structural variants. It's a little bit what I told you before. Take the time to consider, to go out of the box and to get out of this business as usual. Stay curious and get informed. There are many R&D developments, pilot projects which are being built. Norms also within the Eurocode 3 committees, we're working on adapting the norms to consider all of these new developments. But things are moving quite fast, and so it's important for any involved party to really be willing to learn about that. To rely on what is available today, and now I come back a little bit to the decarb of the industry. Understanding the supply chain, once more discussing with the suppliers, and understanding that there are some things which will be available in a couple of years, not yet ready, and that there are other things which are available today and that you can use today. So, for example, the EAF products and using high grades to decrease material quantities when it makes sense. To request EPDs, take time to understand them, and to support entities with a robust industrial roadmap showcasing a real climate commitment. So here I have given you an overview of what we do, but as a customer, you also have a responsibility when you select the supplier you want to work with. If you choose a supplier that has a robust industrial roadmap and a clear engagement, a clear commitment, then you know that actually when you buy from that supplier, you are indirectly contributing to the efforts. So this is somehow a little bit linked to the point number one. Really, I strongly encourage to have a communication with the manufacturers to understand the challenges and the opportunities. And of course, on the right part of the slide, keeping in mind to play the strength of each material. There is no perfect material. To evaluate the whole system and not single elements, considering other constraints such as cost, fire, earthquakes, depending on the area, and so on. So that's the main messages for me.
Thank you, Marion. You mentioned that it is important to understand how steel products are made. Do you think the designers or, let's say, contractors or whoever buys your product understands actually how they are being made, or do they just buy steel?
It depends. It depends. And I would say also, coming back to the question you asked me before, that it's we see a huge shift now. We have more and more people being willing to understand. So now we have a lot of discussions with the stakeholders who are willing to know more and to understand, which was really rarely happening in the past. So definitely there is a good trend in that direction, but still there is still a huge need for education, because there are still many people who do not know how we produce concrete, cement, steel, and so yeah, we really want to push for more education and more transparency in that field.
More education is always good. We have some questions here from the clients, or clients audience. Sorry, might be client. I don't know. I just go. There's not too many. I'll just go there from the order.
But just maybe before you go there, I have a question for the audience before we pass to the Q&A. So it's more, I'm just gonna publish it, so it's gonna appear on the screen. And the question is, if anyone from the audience would like to book a demo with One Click LCA to learn more on how to proceed and advance in the sustainability journey. So please answer, and after this, we will just jump onto the Q&A live.
Great, thank you. So yeah, if you want to know more about EPDs or any carbon calculators, really. So I have a question here which was voted highest and also came at first. How is the availability of scrap steel to produce construction steel? Is the availability is it available everywhere, or is it localized maybe?
Is it problematic or not? I would say that there is no shortage of scrap today. Europe is net exporter of scrap. So today, really, our supply chain is facing no issue when it comes to scrap availability. No, of course, we need to use the scrap mindfully and to use it well. I think it is not realistic to have this simplistic view of saying, okay, everything needs to be EAF and we just recycle and that's it. Because the steel demand is gonna rise in the coming years, and even today we don't have enough scrap to face all the steel demand. So this is why primary steel making is still needed, but it's a quite complex topic in a sense that here we talk about construction. All of the construction products can be manufactured with EAF. But some of them are still made through the blast furnace route. But when we go outside of the scope of construction, if we go, for example, for automotive or other applications, the requirements may be more stringent, and we really need to go through primary steelmaking. So, long story short, I mean, we can talk about this for a very long time, but we need to decarb both primary and secondary steelmaking. That is certain, and we can. It's not enough to just rely on recycling. Nevertheless, today we have no bottleneck issue when it comes to the sourcing of our scrap. Here in Luxembourg, where we produce our xcarb sections, we source our scrap from a radius of roughly 300 kilometers around Luxembourg, so only just in the neighboring countries. And so far we see, also with our people working in a supply chain, we see no issue in terms of being able to provide our xcarb recycled sections to our customers.
Okay, so we have enough scrap in some places at least, and can be also local. There's also a question about the price difference of xcarb and regular steel products. Is there a massive difference?
There is a difference, but it's not massive. So very transparently, I'm not a salesperson, so I'm not the one who makes the prices. But what we usually tell to the people as an order of magnitude, if I take as example our sections, is that we can expect roughly 50 euros extra per ton of steel, which is not much. We have made the assessment for an office building of 8 levels, if I'm not mistaken. And this, for the whole project, was leading to between 1 and 2 extra euros per meter square for the whole project. So it's definitely an extra cost, but it's not something that completely changes the balance. No. And it is today an extra cost, which is actually asked to fund the purchase of renewable electricity. So hopefully in the future this will change, but today we are asking this a little extra, yes.
Okay, but yeah, it's not complete prohibitive. There's also a question if the xcarb products are available worldwide.
So I would say then yes. They're not produced in every country of the world, of course, because we have our production site in some countries, but we ship regularly worldwide. Today we have been talking a lot about Europe, but we also work together with the collaborators in Australia, Southeast Asia, the USA, Middle East, and we ship our beams so on vessels. So this is definitely doable. And we also have some production sites outside of Europe, of course, but depending on the products that you want to get, they are produced in some given countries.
Okay, we have maybe time for one more question here. Maybe one more about the facilities. So do your steel facilities run into issues regarding the amount of power required to run the EAFs?
No, I mean, it's another complex topic that I will try to tackle to the best of my capacity. If the question is targeting the renewable electricity, I think it's important to mention that we're working with PPAs, so power purchase agreements, so that we have these contracts with the energy supplier to make sure that we can access the required quantity of energy. And the PPAs also work as some kind of incentive, because, of course, when we want to commit to use a certain percentage of renewable electricity, this encourages the energy company to create more renewable electricity. And we also have some projects in collaboration with local governments. It is the case, for example, in Spain and in Germany, where we are collaborating on building solar farms in Spain and offshore farms in Germany, so that there is this notion of additionality, that we are generating extra renewable electricity that we will be using in our production sites. So, and it's a little bit what I referred to when I mentioned the xcarb Innovation Fund, that we realize that we have a strong link to the sourcing of energy, and we are really willing to make sure that we also take part in this energy revolution, and we're not just using from everybody else, we're also making an effort to contribute to generating extra renewable electricity.
All right. Thank you. I think that answered that. Obviously, how do you see, just to ask one question for about one-click LCA at the end, and then we finish. Do you think tools like LCA tools and EBD tools like ours, how do you see them to shifting the industry? Do you think they are done some good in the industry?
Yes, we definitely use it in-house. We have several licenses. And to be honest, we use them under two angles. We use them with our R&D team, and we use them within Steligence, so this technical assistance team. So we use them to help to make this LCA quick and easy LCA of the projects we're working on, but also to run some sensitivity analysis and developments which are more into the research frame, but which are definitely helpful to understand, like make these hotspot analysis and really put the finger where to make us aware of where we should insist and make maybe deploy new structural systems and things like this. So we're using it quite regularly, yes.
That's good to hear. I think that's the wrap then. It's up. Anna?
Yes, we can wrap it up, and we can follow up with the questions that remained unanswered. So basically, yeah, so no question will remain unanswered in the long run. So we will definitely come back to them later on. But this is quite an insightful presentation and very stimulating conversation. So thank you everyone for joining, and hopefully see you in the next one.
Thank you.